today I'm talking about this fully nonlinear Hessian-dependent functionals with free boundaries. And let me tell you just, yes, so let me just tell you the people that helped me in getting through this journey that I'm sharing with you this afternoon. So the results I'm telling you today were obtained in collaboration with Pedro Andrade and Julio César Correa. Pedro was a PhD student at Catholic University in Rio de Janeiro, and she's currently working in ICMC USP in São Carlos, and is fortunate enough to work under the supervision of Professor Ederson. And Julio is graduated recently from the Universidade Federal of Rio de Janeiro, and is currently a postdoc at Catholic University, and both very talented, very sharp mathematicians. A privilege for me to learn from them and to talk about these things this afternoon. Okay, so what's in the menu? What's the outline for today? So the thing today is this. I'll start talking about Hessian-dependent functionals, and we are interested in minimizing those functionals in certain spaces. And what happens is that if we consider the first compactly supported variation of those functionals, then we end up with PDEs, right? We end up with Euler-Lagrange equations. And in the particular case, in the concrete setting of Hessian-dependent functionals, this Euler-Lagrange, they are very particular. And they are particular in the sense that they are fully nonlinear mean-field games. So I'll talk a little bit about what are mean-field games and fully nonlinear mean-field games, so the audience somehow gets acquainted with this class of problems. But then you see, we start with Hessian-dependent functionals. We do some trick to get a PDE. The PDE turns out to be a fully nonlinear mean-field game. But then you see, in the context of minimizing functionals, you can somehow add a perturbation, not really a perturbation, but you can add a term in line with this Bernoulli problems that equip the entire problem with the entire setting with a free boundary, right? And then, well, what happens here is that on the one hand, you want to understand the regularity of the solution and properties of the minimizers. Somehow those things are interchangeable in the sense that those objects are the same. And you also want to get as much information as possible on the interfaces or the free boundaries. So we'll start with Hessian-dependent functionals. We'll have some times to handle with, to deal with a PDE system. And at some points, a free boundary appears, and we are interested on the regularity of the solutions, minimizers, and on geometric properties of the interface. To conclude, I'll talk about some ongoing research and some open problems we've been, I would be more than glad to share with you, and of course, discuss with you in due time if you're interested. Okay, so Hessian-dependent functional. So for us today, what we have is this. We grab our favorite fully nonlinear operator, we evaluate it along the Hessian of a function, let's say U, and then what we do is, you see, we get here and we raise the whole thing to a power P. You have an operator evaluated along a Hessian, you raise to the power P. What else can you do? You can integrate over the unit ball or your favorite domain in RD, let's say omega or something like that. And well, you have this integral, but then you say, well, I have this integral. What if the function is positive? What if the function is negative? Then one thing you can add here is indeed this term. And this term, what it does is it computes the measure of the set where the function is strictly positive and penalizes the functional. Capital lambda penalizes the functional with this measure. So for us, capital lambda will be a fixed number. There is either 0 in the setting where we don't have free boundaries, or strictly positive where we have free boundaries. And capital F will be a lambda elliptic operator. And by lambda elliptic operator, what I mean is that by a strictly greater than 1 lambda fixed, what we have is these two inequalities mutually satisfied. So what happens here is, if you're on top of a symmetric matrix M and you move in the positive direction N in the space of symmetric matrices, not the positive, right? The semi-definite positive direction N, then these inequalities are mutually satisfied in the sense that the growth of the operator F is somehow controlled by lambda and from below by 1 over lambda, right? And then what we want to do, we want to minimize the functional in some Sobolev, some appropriate Sobolev space that also encodes a boundary condition that is considered also in the sense of Sobolev. Right, so we'll have here a function g, and the importance of this function is that you see somehow, if you don't have this function, then u equals 0 could be a minimizer, and we want to get rid of this kind of pathologies, right? And what we want to do, as I said before, and I'll try to emphasize it again, what we want to do is to prove facts about minimizers. There will be PDEs and therefore solutions, and also as much information as possible we want to obtain on the associated free boundary, right? So you see, one thing is you can define whatever you want and you can start studying whatever you want, but a very nice aspect of what we do is to motivate the problems. And so in the next couple of slides, I'll try to convince you that Hessian-dependent functionals appear naturally and are in fact interesting objects for us to study. So you see, we'll start with this example, the biharmonic operator. And the biharmonic operator is very simple in the sense that what you do is you minimize the L2 norm of the trace of the Hessian, right? So you take the Laplace operator if you want, you take the absolute value raised to the square, integrate on the P1 or again over your favorite domain, and then you want to see what happens with these guys. So you see, if you compute the Euler-Lagrange associated with this functional, then you end up with the biharmonic operator, which is the Laplace of u hit once again by the Laplace, and then the equation here that appears will be the homogeneous thing. So this would be the biharmonic equation. Right? Why is this interesting? Well, the first thing is that, well, this is interesting in the context of conformally invariant energies, because if you pay close attention to this guy, then it's clear that this would be, well, it's clear, it's not that honest, but it's true that this energy will be conformally invariant in dimension d equals to 4. This is interesting because you see, if you have the framework associated with the P Laplace operator and therefore the P Dirichlet energy, it would be also conformally invariant in dimension d equal to P, right? Here it's fixed, d equals to 4. And one important question that one can ask concerning the regularity of biharmonic maps is, you see, you have a minimizer of this functional that goes from RD to a target space. There is the n-dimensional sphere, right? And then you want to understand the regularity of this class of problems. This type of questions, they have been asked by very, very smart and very interesting people in the community. By, I mean, just to mention a few examples, I mentioned these two papers by Sun Young, Alice Chang, Paul Young, and their collaborators. Both papers from 1999, where a fundamental study of the regularity theory for biharmonic maps into the sphere is developed, right? But then again, one can say, well, biharmonic operators, very nice theory, but not in the cards for me. Let me try to continue motivating you to consider Hessian-dependent functionals. So you see, one important thing when you're trying to minimize things is convexity, right? Convexity is an important property. If you want to minimize things and you don't have convexity, then maybe this is not the correct thing for you to minimize. So suppose you face something like this J of u, which the gradient squares, so some sort of resembles somehow the usual Dirichlet energy, but then you have this -1 raised to the square. So this thing is not a convex functional with respect to the gradient. And then, well, what can we do? right? What we can do is some sort of a convex variant of this guy. There would be a J epsilon where we epsilon perturb the functional by adding epsilon to the square, the norm of the Hessian raised to the square as well, right? So here what we have, you see, we have the higher order term is convex. The dependence on the higher order term is convex, and then a nice theory can be actually performed, and then we can tackle these things with usual strategies. So this functional in particular, this J of epsilon, is known as the Avle-Giga functional. And one of the important questions here is to send the parameter epsilon to 0 and then deal with the limiting complications that might arise, right? And here I'm talking about the so-called microstructures that can appear. Right, the reference for this type of functionals would be 2 papers by Patricio Avilés and Yoshikazu Giga. They appeared in 1987 and 1996. Right, but then again, non-convex functionals, biharmonic operators, well, maybe not the most interesting thing for everyone. So that might be the case, that the mechanics of solids is more appealing for some of you in the audience. So let me try to tell you why Hessian-dependent functionals also appear in this context. So you see, if you have a rubber band and you twist the rubber band, usually in the middle, what appears is a number of wrinkles, right? And why is that? So one way to address this, to try to answer this question or to address this issue, is through an energy minimization process. So suppose what you're trying to model is a rubber band being twisted, and you want to understand what happens with these wrinkles in the middle of the rubber band. So the functional modeling, this type of things, this type of phenomenon, amounts to 2 tensors. The first tensor m, and depending on u, raised to the power 2, plus something, an h to the square, times the norm of a tensor that behaves as the norm of the Hessian to the square, plus a constant, right? So this is another instance where this type of functional appear. And you see, another instance in this context of mechanics of solids has to do with blister formation. And you see the example, I think this is the workhorse example. Like you have a book and you want to protect the cover by applying a contact film, right? So what you want to do is apply this film to the cover of the book, and then you're a very careful person. You try to do it avoiding these small bubbles, these blisters that appear, right? And then you try with a ruler, trying to be very careful, trying with a needle to kill the blisters. But you see, the underlying phenomena is slightly more complicated. It has to do with unmatched elasticity between the materials. What happens is that you see the elasticity of the thin film and the elasticity of the book cover differ. And the way nature found to match this mismatched elasticities is to create blisters as an energy minimizing process, right? So this is another instance where this functionals appear, and the fundamental questions have to do with matching upper and lower bounds as this parameter h goes to 0. By matching upper and lower bounds, I mean lower bounds from above and below their scale with the same degree of homogeneity. And here we can find a very interesting and nice list of references: Jacob Bedros and Robert Kohn, Sergio Conte, Maggi, and Stefan Miller, Kohn and O'Brien, and so on and so forth. What we have here is, in fact, an account of mechanics of solids through functionals depending on the Hessian of interesting or important quantities, right? Very nice. The last, I mean, I find these applications to be very interesting, right? And the last thing I want to mention to you, also in line with the topics of this workshop, is an application in geometry concerning the area functional, right? So what happens is that if we have the area function, there's nothing but the square root of this determinant. Once again, an instance where the Hessian appears. Then what happens is that critical points to this functional are closely related to Hamiltonian stationary equations and minimal surfaces through the Lagrangian surfaces, right? And there are two interesting references about it. They are apart almost 30 years. This first paper by Yong-Geun from 1993, where most of this theory is tackled for the first time. And this very recent paper by Arunima Bhattacharya. And the reason why I mentioned this paper is that it has a very close connection with regularity theory. And what is proven here is that if you have C11 minimizers, they are of class infinity, right? And the way the proof goes is you start C11, you get C2 alpha, and from C2 alpha, you go to C infinity. And I find this to be very much alike the proof of the Evans-Krylov theory, the Evans-Krylov regularity theorem, when you have viscosity solutions, right? Because the first thing is you get C11, and from C11, you go to C2 alpha. In the concrete case of this paper by Arunima, what happens is that once you have C2 alpha, there is some bootstrap that gets you C infinity. But this jump from C11 to C2 alpha, I happen to find very, very beautiful and very interesting. Good. But you see, what we are doing today is to connect Hessian-dependent functionals with this class of problems called mean field games. And how do we do it? Well, the first thing is to consider the first compactly supported variation of the functional, and this is just a fancy name of let's get the Euler-Lagrange equation, right? So when we get the Euler-Lagrange equation, something very weird happens, because you see the functional depends on the Hessian. So here we have the derivative of the operator f with respect to the ij entry of the matrix. Here we have the operator, and everything is evaluated along the Hessian, right? But the thing is, we have to heat these guys with two derivatives, derivative in the direction I and direction j, and then sum everything with respect to I and j from 1 to d. Right, so the thing is that, in fact, we end up with the fourth order equation, and I humbly acknowledge the fact that I don't know what to do with the fourth order equation, right? So we have to somehow do something else to study this problem. So you see, one thing that we can try to do is to give a name. This is a variant, almost biblical, right? Let's give a name to f d2u raised to the power p minus 1. Let's call it m of x, right? So if we do this, we end up not with one fourth order equation, but with two second order equations, right? The first equation here is the fully nonlinear equation for u, and m happens at the right-hand side is a source term, raised to some power, but we don't care, right? The other equation is a double divergence equation whose coefficients are Fij evaluated along the Hessian. Well, you can argue that we don't have a lot of information about the Hessian. How do we know what's going on with those coefficients? You see, we have ellipticity for f for the operator f, so these guys are bounded. So we had one fourth order equation, and now what we have is one fully nonlinear equation coupled with another second order equation, and is the coupling term for the first guy, and Fij d2u is just a set of coefficients for the second equation, right? But this is very good. This is very good because we know things about fully nonlinear equations, we know things about double divergence equations, but it's even better because you see, if you take the linearization of the first equation in the system and you compute its formal adjoint in L2, in the L2 sense, then you end up with the second one. So the system is set to satisfy an adjoint structure, and in the presence of an adjoint structure, improved regularity appears. right? This is a fundamental property of this class of problems. This is one of the things that characterize mean field games, right? And because this is driven by fully nonlinear operators, what we say is, well, we are here in the presence of a fully nonlinear mean field games. Fully nonlinear mean field game. So there is a very extensive and virtually impossible to mention list of reference for this class of problems. And then what I want to share with you is just the two main references when it comes to the first papers. This class of problems was introduced by Jean-Michel Azri and Pierre-Louis Lyon circa 2006. In a series of papers. I think there are two papers in 2000. It's not that I think, I know there are two papers in the Compte Rendu in 2006 and 2006, and one paper in the Journal of the Japanese Math Society in 2007. Right, and here the remaining references are monographies or books. They're very much tailored for people who are interested in the field. So we have this work by Pierre Cadalha-Gué, the book by Alain Bensoussan and his collaborators, our book with Diogo Gomes and Varda Voskanian. There is this beautiful account of the probabilistic aspect of mean field games by René Carmona and François Delarue. And there's a recent set of lecture notes edited by Pierre Cadalha-Gué and Alessio Porretta, which actually point to the future in this class of problems, in the sense that these guys managed to get together very interesting authors talking about this class of problems in a very neat way. Good. So you see, we have the functional, and now we have the PDE. We are lucky enough. The PDE is in fact a fully nonlinear mean field game, and that's a system we hope we know how to tackle. Right. So let me now that we know what's going on, let me share with you a few results we managed to produce in collaboration with those lovely individuals I showed you at the beginning. So first, what we consider is this interplay of the functional, where we have information on the minimizers, and the fully nonlinear mean field games, where information is on the solutions, right? So there will be occasions where the minimizers aspect of the theory will be binding, and then we'll recover information for the solutions, and the other way around, where the solutions will be where the information appears, and then we'll take it to the context of the functionals, right? So let me start here with the fully nonlinear mean field games in the absence of free boundaries. So if you pay close attention here, what we have is capital lambda is identically 0, so we don't have free boundaries, and everything happened in the entire domain. So let me start with the existence of solutions. So the theorem, it was done jointly with Pedro Andrade, and is to appear probably this year or the next one, but I'm sure the date is 2021. So what happens is this: we have lambda is 0 in the functional, and capital F is well prepared in the sense that it satisfies the ellipticity condition and some natural growth conditions as well. So we suppose P is either D or strictly above, and then what we can prove is the existence of a pair U and M satisfying the following. U is a continuous function solving the fully nonlinear equation in the mean field game system in the viscosity sense. In particular, here, to be more precise, it solves the mean field game system in the LP viscosity sense, right? And this is so because you see the source term M is there. Well, there's no reason why we should suppose this thing is continuous, right? So when I say here viscosity sense, I mean in the LP viscosity sense. M on its turn is an integrable function that solves the double divergence equation in the mean field game in the distributional sense, right? So the funny thing is, well, for the first, a solution will be a pair that solves the first equation in the viscosity sense, in the LP viscosity sense, whereas M is a distributional solution for the double divergence equation. So this is the first result about the system, and the result about the system, of course, stems from the functional, right? So let's try to see how the proof of existence goes. So here we want to apply the direct method in the calculus of variations to produce minimizers for the functional. And the first thing is, well, we need coercivity, and we also need weak lower semi-continuity. So some work has to be done here, and well, it's doable. And once this is done, we get the existence of minimizers. But you see, once we have the minimizers for the functional to produce solutions to the PDE, there's a work to be done, right? And a way to put it is to say, well, the solution you find that you don't know yet the solution has to be a solution, right? So solutions, they have to be solutions. And there is a routine one has to perform in this concrete setting. And what happens here is, well, you have to notice and you have to prove that minimizers are in fact solutions to the mean field gain system. So the first steps to notice the regularity of view coming from the minimization process allows us to define the function M. So we can in fact define M almost everywhere as F along D to U raised to some power. Once this is done, U becomes a strong solution to the fully nonlinear equation. And then we have to make the strong solution notion. This has to be somehow related to the LP viscosity, thing. And this is done through an application of the Bonis-Maximi principle, as stated by Pierre Lyons in a very nice paper from 1983 in the proceedings of the AMS, and according to the argument of this very beautiful paper by Luis Caffarelli, Michael Crandall, Maciej Kotze, and Andrzej Wiech in CPAM 1996. So I mean, the thing is, you start with the minimizer. Minimizers allow you to define M as you want. Then you have a strong solution to the fully nonlinear equation. It becomes an LP viscosity solution. And at the end of the day, M is, you can write the identity that ensures that M is a distributional solution to this problem. And so that's what gives you the existence of solution. The existence of solution at first was something very challenging for us, but once it was written, we had this feeling that, well, now that it's done, and we feel it's an easy thing. So what else can we tell about this guys, right? So there is one interesting thing here that is about improved regularity in Sobolev space for the function U that is very much related to the double divergence equation and actually to the mean field coupling, right? So let me share this result with you. So once again, lambda is 0, we don't have free boundaries, and F is well prepared, whatever it means, right? If P is above the dimension over 2, then if we have a solution UM to the mean field gain, U is in fact in W2 this exponent d over d minus 1 times p minus 1 locally in the unit ball, and we have an estimate that is controlled by a universal constant, and in terms of the L infinity normal view, which somehow encodes the boundary data, and the L d over d minus 1 norm of M raised to the power 1 over p minus 1, right? So you see what happens here? What happens here is, if you have fd to u equals to mu raised to 1 over p minus 1, I mean, if you have the first equation in the mean field gain, and only the first equation in the mean field gain, given that the right-hand side is a function in L1 raised to that power, you don't have this regularity. What you have is W2 p minus 1. If you're outside of the realm of mean field gains, you have W2 p minus 1, right? If p minus 1 is above d minus epsilon 0, where epsilon 0 has to do with this beautiful constant called Scauria's exponent. Here you can do better, right? Here you can do better, and you can do better by a factor that is solely dimension dependent. There is d over d minus 1, right? And where does this factor come from? Well, this factor comes from a combination of two classes of techniques. So the first one is, well, we want to use ellipticity and elliptic regularity by approximation or perturbative methods as introduced by Luis Caffarelli in his paper in the Annals of Mathematics, 1989. And we recently learned from Maria Soria Carro that these ideas appeared also in 1988 in a set of lecture notes by Luis Caffarelli, published in a journal edited in Milan. And well, approximation or perturbative methods, as introduced by Luis Caffarelli and developed by a few authors, Li Hewang, Ovidio Savin, Cyril Imbert, and Luis Silvestri. And I have to mention, separated, a substantial and very successful effort led by Eduardo Teixeira and José Miguel Urbano and Damião Araújo and their collaborators recently, in which a very wide range of problems has been attacked and in a very successful way, right? If you ask me, I find this very particular paper, Eduardo Teixeira and José Miguel Urbano, 2014, and the analysis and PDs, a very nice paper for one reason. I mean, this is the paper where approximation methods meet intrinsic scaling, and the miracle happens, right? So I find this literature very, very appealing, and as a tribute to this developments, as a tribute to those who did very nice things before. We just finished recently this monography that is entitled Elliptic Regularity Theory by Approximation Methods, and is to appear recently as a volume in the lecture notes of the London Math Society. I ask you please to get hold of this file, and if you can help me get it into some of these lib something websites, I'll be very grateful. And well, the other pillar of this improved regularity result is the improved integrability for the double divergence equation as produced by Eugene Fabes and Daniel Strukens. This is a wonderful paper from 1984 in Duke Math Journal. And what happens here is that indeed these authors are considering the double divergence equation as the adjoint of the trace of a matrix times the Hessian, and then trying somehow to obtain information on Green's function, integrability, and reverse Hildering inequalities. It's a tour de force and somehow a tour de France in the sense that it covers the entire territory and gives a lot of information. So we use the elliptic regularity by approximation methods combined with improved integrability for the double divergence equation through a lemma that has to do with improved integrability for the equation driven by Fij d2u, the equation for M. So what happens here is that if we have a solution to the mean field gain system, so instead of being in L1, the function M will be indeed in LD over D minus 1 locally. And then what happens is that indeed you get this D over D minus 1 factor in the W2Q regularity for U, right? So put simply, if M is in L1, the equation, the double divergence equation, implies immediately that M is in LD over D minus 1. So let me continue with the case of free boundaries. So if we go to the case of free boundaries, the functional, let me recall the functional. Now, the capital lambda is a strictly positive number, and we once again derived through a first compactly supported variation, the mean field gain system, but no longer in the unit ball. Now it takes place in the unit ball inter the positive phase, right? And this is tricky. This is tricky because you see what happens here is that, well, information we had before, we no longer carry with us to this setting. So the first thing we can tell you is that, well, existence of solutions is something we can prove. The existence of solutions to this system is something we can prove, knowing the proof in the case where free boundaries are not present. Then, well, an intricate adjustment leads you to the proof in this setting as well. But it's an intricate adjustment, but it's an adjustment, right? It's not that you need any new ideas. You just need to use some dexterity in treating the arguments, right? But the funny thing, and what I find to be the more challenging thing, is the lack of information across the free boundary, right? In particular, the improved integrability for the measure doesn't see the free boundary, doesn't reach the free boundary, and therefore never crosses, right? So how does it work? You see, this is a local and interior result. So if you're in the presence of a free boundary, what happens is that a distributional solution satisfies this weak form here, where test function phi is smooth and supportly compacted in B1 inter the positive phase. So this orange thing here kills you at the end, because you see what happens is that you have here, this gray region is where the function is strictly positive. So here in the interior, you have the region, you have the support of the test function here in this ball with the black line, right? But the improved integrability happens only in this region with the dashed line, right? This is the region of improved integrability for the measure. So you see, the funny thing is that this ball, this dashed ball, never sees the free boundary, being this white part, the region where the function is zero. So it never sees the free boundary. As a consequence, you don't cross, right? So the improved regularity is off the table. We need first to produce a result on improved integrability for the solution, and then we were lucky enough to produce this fact. I called it here as a corollary, because if you go through the proof of the existence result, it jumps in front of you. There you can produce improved integrability for M, right? You must have an idea. Indeed, you must have an idea, but it's as if the idea slaps you in the face as you go through the proof of existence, right? So let me tell you how it works. If F here is on top of being well prepared, is also strictly convex, and P is above 2, then what happens is that provided U and M, this pair, is a solution to the mean field gain, then M is in L P over P minus 1 locally, right? So in here, the improved integrability crosses the free boundary. And if we're lucky enough to have P equals 2, then we recover Fabes-Instruct result. And this is actually the highlight when it comes to the information on the minimizers, on the solutions, through the proof of existence, right? The proof of existence, well, it's an adjustment of what we knew, but this adjustment unveils an important aspect of the problem, right? But then you see here, another thing that we have is the information on free boundary. We need, now there's a free boundary. We can either ignore the free boundary because it's really something very, very, very difficult sometimes, or we can try to say something. What I'm telling you today, of course, it's not the whole story, but it's very far from being the whole story. But there is some information we have that we find useful and we'd like to share with you. And this corollary here is a typo, it should be a theorem, just to add some solemnity to these facts. So you see, once again, we have, what is this? No, this is wrong. This is wrong. This is completely wrong, and I'm sorry. If lambda is 0, there's no free boundary. It has to be strictly above 0. I mean, this copy and paste thing is hunting me back, and I apologize for that. But here the fact is, lambda is strictly positive, F is well prepared, P is equal to dimension, then the reduced free boundary is a set of finite perimeter. And not only that, but we have a very weak free boundary condition for the solution in terms of lambda, the dimension, and the operator F and its derivatives, right? So what's being said here, what we are saying here has two instances, right? First, we are telling you what's the boundary condition, the free boundary condition. It's a very nonlinear type of Neumann thing, what's happening as you approach the free boundary. But we are also telling you the reduced free boundary is a set of finite perimeter. What meaning the following? I mean, it's quite interesting to have this type of information, but we would like to have something else to add here, right? So as we speak, I guess Julio Correa and Pedro Andrade, they are very much focused on a density estimate that builds upon the finite perimeter of the reduced free boundary to give more information on this object. I mean, this is just something we started doing, but I'm sure there is much more things to be tackled here, right? So how well, for every vector field compactly supported and say infinity. So how do we prove this type of result? So we start with an appropriate variation. So given a smooth compactly supported vector field and a small parameter t, we construct a diffeomorphism and a competitor. And of course, it's a theorem to see that psi t is a diffeomorphism and ut is a competitor, right? And once we have that, because we have proven that ut is a competitor, then we know from the stationarity of u that this derivative is 0 when t is equal to 0, right? For t equals 0, this derivative is 0. And then hell breaks loose in terms of computations. We have to do a lot of computations, but at the end, we derive the free boundary condition. When it comes to the finite perimeter, the key unlocking this type of results is an epsilon estimate for the reduced free boundary in terms of the Hausdorff measure. And this estimate goes as follows. I mean, for every epsilon, there is a strictly positive, we can find a positive constant such that this integral is with respect to the super level set, the reduced boundary of the T super level set grows at most as epsilon times this constant. Great. Okay, so this is how we prove the result, and this is the set of things that we know about these problems. There are two things that I'd like to share with you that I find to be very interesting open problems, and things that I'd like to share and to discuss if you're interested in the future. So the first thing is, you see, when I mentioned this motivation, the biharmonic maps, I mentioned biharmonic maps into the sphere, right? What if we consider, instead of biharmonic maps into the sphere, biharmonic maps into the cone? Here, CM would be a cone over the m-dimensional sphere, right? And the question here is once again on regularity theory, but you see, if you are away from the singularity, if you are away from the vertex of the cone, of course you're smooth and everything is known and you're regular enough and everything. The question is, what can we tell about the pre-images of the vertex? Is there any way we can quantify, or is there any sort of partial regularity result that we can say that things are smooth except on a set whose Hausdorff dimension is controlled, or this kind of stuff, right? Does biharmonic maps into the cone have line defects, point defects, and this kind of questions would be the interesting questions here, I think, right? And the other thing, the other open problem, I know in the audience, people, this is the last thing I'm telling you today. I hope I'm not going too much above the time I have. And well, the other thing I'd like to share with you, and I'm sure in the audience, people, there are a lot of people that know about the P Laplace much more than I do, is a statement according to which the P Laplace equation is a mean field game, right? And why is this crazy statement? Why does this crazy statement make sense? So let me tell you this. Fix P and consider weak solutions to the P Laplace equation, right? A very simple thing. The divergence of the norm of the gradient raised to the power P minus 2 times the gradient, right? Everything equals to 0 in B1. Right? We know a few things about this equation, and one thing that we know is that the gradient is not only continuous, it's locally Hilbert continuous, right? So it's a function. For some alpha, I don't care, it's continuous, right? It's a function, it's a non-nest function. It's a continuous function. Well, if this is a continuous function, why not to write m of x as the gradient of u raised to the power p minus 2, the norm, evaluated at x, right? This could be. But if we do this, we get a system. We get a system, there is an iconal equation for u. This is the first equation here, right? An iconal equation for u whose right-hand side is m raised to some power, coupled with a transport equation for m, whose transport term is the vector, is a very special vector field. It's the gradient of u, but it's just a vector field. This is just a transport equation, right? And well, why is this interesting? This is interesting for two reasons. I mean, the first reason is, well, we know a lot of things about the Laplace operator. We know a lot of things about the mean field game systems. What if we combine those things? Oh, I forgot to mention, this is a mean field game system, right? This is a mean field game. If you linearize the equation, take adjoints in the appropriate functional spaces, then from one you go to the other. And well, we know a lot of things about the Laplace operator. We know a lot of things about the mean field game theory. What if we put those things together? Is it possible to do better in one or the other direction, right? One particular instance has once again to do with regularity theory. You see, what if by resorting to a mean field game formulation of the P Laplace equation, we get an optimal C1 alpha star regularity result? And here by result, I mean, you have the modulus of continuity and you have an estimate. You have an estimate, right? And then you see, well, this estimate is such, this is not the estimate, but the exponent is such that alpha star is strictly above 1 over p minus 1. Then, as a consequence of this fact would build upon a well-established and well-understood framework due to Damião Araújo, Eduardo Teixeira, and José Miguel Urbano, and would allow us to prove the CP prime regularity conjecture for the solutions of the P-Poisson equation with the bounded right-hand side in n dimension, right? And dimension is with an S, not with a T. I'm sorry for this. This is the third typo of the third typo, right? That's the German one. And well, this is a very ambitious plan and program, but we'll have very consequential results to the literature on regularity theory for the P-Poisson equation, right? I mean, the idea of sharing open problems with you is not only to say where things could go, but it's always a way to say, well, there is more reasons for us to get together in the future. I think this is what makes the profession more and more interesting. And it's one of the things that I miss the most. And on that note, I thank you very much for your attention.